Welcome back to the Deep Dive. Today we're going to get into a very specific piece of infrastructure tech.
We are. It's the Thor Broadcast F-SattGalaxy kit.
And our mission here is to really unpack how this thing solves one of the biggest signal distribution headaches you find in modern construction.
It's a huge headache, and it's really about the sheer volume of cabling.
Right.
I mean, when you're moving high bandwidth signals, especially multiple satellite feeds, they're called L-band signals.
Well, that's another one, right? A terrestrial signal.
Exactly, like your local off-air TV.
Yeah.
You traditionally end up with this massive, and I mean massive, bundle of coaxial copper wire.
And just so you, the listener, are clear, when we say 4 L-band signals, we're talking about what comes directly from the little receiver heads on the satellite dish, the LNBs.
That's right.
Yeah.
So normally, to get those 4, plus the terrestrial one anywhere, you need 5, sometimes even 9 separate bulky coax cables.
Which is just inefficient.
Okay.
It's expensive, and the signal degrades the longer the cable is.
Absolutely. So the initial big takeaway with this system is just how transformative it is. It takes all 5 of those signals and collapses them.
Into what?
Into just one single-mode optical fiber.
Okay, let's stop there. How do you cram 5 separate live broadcasts onto one single strand of light? I mean, without them all just bleeding into each other.
That is the core technology nugget right there.
So what is it?
It's something called coarse wavelength division multiplexing, CWDM.
Okay.
Instead of using different frequencies, like with radio, the system uses different colors of light, different wavelengths.
So each signal gets its own color.
Basically, yeah. Each of the 5 inputs is assigned its own unique laser, its own optical lane on that single fiber highway.
That sounds incredibly efficient, but maybe a little delicate. Are you just shifting the point of failure from a simple copper cable to some, hypersensitive optical hardware?
That's a critical question, and the engineers have thought about it. To maintain system integrity, they built in automatic gain control, AGC.
And that does what?
It actively stabilizes the output signal level, so it smooths out any little fluctuations that might happen over distance or from temperature changes.
And the physical plugs, the connectors. Optical connections can be tricky. If they're not perfectly aligned, you get reflections, signal noise.
They've addressed that too. They use a very specific type of connector, an angle polish SCAPC connector.
Shield.
Yeah, the angled contact point means any light that tries to reflect back gets eliminated, so you're left with a much cleaner, much more stable link.
That level of detail is what lets this thing work at a massive scale, I'm guessing. So let's talk about that distribution capability. It's not just for one long cable run, is it?
Not at all. The transmitter has a really high optical output power. It's designed for serious capacity. It can send that main signal out to as many as 32 optical receivers.
32. And how far away can they be?
All within a 10-kilometer radius.
So this is a perfect solution for an MDU, a multi-dwelling unit. Think apartment complexes, business campuses.
Exactly. It's an excellent 1x32 MDU distribution solution. And think about the smell. When the light gets to one of those 32 points, it's converted back to the 5 original RF signals.
And from there, it feeds a local system.
Right. It might feed into a building's internal network, replacing those super long, problematic coax runs you'd normally have from a dish on the roof down to, say, a swim switch in a basement.
So when you add up all the outlets in those 32 locations,
the total number of subscribers can easily top 1,000.
So to sort of synthesize this for you listening, the efficiency here comes from, moving signals from bulky copper to light. And then using that CWDM tech to keep all 5 signals perfectly separate while they're traveling together.
It's an incredibly elegant solution for a big logistical problem.
For sure.
And, the sources mention that this 10-kilometer maximum range isn't an arbitrary number. It's calculated using these complex optical power budget methods.
Yeah.
So this raises a really interesting final question for you to think about. What other invisible constraints, like this optical power budget, govern the limits of our modern connected world? And how does specialized engineering like this keep pushing those limits further and further out?
A great thought to leave on. We'll see you next time.